Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
Welcome back. This is week 9, part 2. So last time we scratched the surface of the magic behind generative adversarial networks, or GANs. Today, we're going way deeper. We're going to talk about the advanced architectures that took GANs from this brilliant, but let's be honest, notoriously unstable idea to the powerhouse tools that create the photorealistic images you see everywhere. We'll get into the core challenge. How do you make them both stable and powerful? It's a story of divergence, geometry, and how we finally figured out how to control what they create. All right, so let's break this down with a metaphor that really clicks. Think of the whole GAN training process like a student. That's our generator, trying to fool a very sharp teacher, our discriminator. The student is forging art, and the teacher's whole job is to spot the fakes. The student only gets better based on the teacher's feedback. But what happens if that teacher becomes, perfect? What if they can spot every single fake every single time without fail? Well, that right there, that's the core problem. The student gets zero useful feedback. They're just told, no, that's a fake, that's it. No hints, no clues about why it was a bad forgery. In the world of GANs, we call this the vanishing gradient problem. Just look at the graph here. When the discriminator gets really, really good, when its output for fake stuff approaches 0, meaning it's 100% sure it's a fake, the generator's learning curve just flattens out. It goes to 0. It's this crazy paradox, right? The generator stops getting better precisely because its opponent got too good at its job. Okay, so here's the plan for today. First, we're going to really dig into that vanishing gradient problem. Then we'll look at the super clever math fix called the Wasserstein solution. After that, we'll jump into the actual architecture, stuff like DCGAN. Then we'll see some real magic with CycleGAN and get into the nitty-gritty of artistic control with StyleGAN. And to wrap it all up, we'll see where GANs fit in the grand scheme of things with something called the generative trilemma. All right, let's kick things off with section 1. We're going to get to the bottom of this so-called original sin of GAN instability. So why do they break? Well, it turns out the answer is a mix of some tricky geometry and the specific math they use to measure distance. So to get the intuition for this, think about it like this. Imagine the collection of all real images is one island, and the collection of all your generated fake images is another island. In the vast high-dimensional space we're working in, these two islands almost never overlap. Now, for a good discriminator, drawing a line in the water between these two islands is, well, it's pretty easy. But here's the catch. In that big, empty ocean between the islands, the landscape is totally flat. There's no hill to climb, no slope, basically no gradient to tell the generator which direction to go to get closer to the real island. And this is the math that backs up that island analogy. It turns out the original GAN loss function is basically trying to minimize something called the Jensen-Shannon divergence, or JS divergence. Think of it as just a way to measure how different two distributions are. But here is the absolute killer flaw. When those two distributions don't overlap, like our two separate islands, the JS divergence just spits out a constant number. It's always log 2. And if your score is always the same, what's the gradient? It's 0. Poof! Your learning signal is just gone. So, if the way we're measuring distance is the problem, what's the solution? Well, we need a better ruler, right? And that brings us to section 2. And what was, honestly, an absolute game changer for GANs? The Wasserstein distance. This was the big one. Okay, the best way to wrap your head around Wasserstein distance is this fantastic analogy called the Earth mover's distance. Picture this. Your generated images are a big pile of dirt, and the real images are a hole in the ground you need to fill. The Wasserstein distance is simply the minimum amount of work, the cost of all the digging and hauling, to move that pile of dirt to perfectly fill the hole. Now, here's why this is so much better. Even if your pile of dirt is miles away from the hole, you can still calculate the work needed to move it. And more importantly, you get a really smooth, useful gradient. It tells you exactly which direction to start pushing the dirt. Okay, so that Earth mover's idea is great, but trying to calculate it directly is, well, it's pretty much impossible for a computer. But thankfully, some very smart mathematicians gave us a workaround called the Kantorovich-Rubinstein duality. Now, don't worry about the name. What it does is give us a dual form of the problem that we can actually solve. This is where we swap out our discriminator for a new thing called a critic. Instead of just saying real or fake, the critic gives a raw score for how real something feels. But there's a crucial rule it has to follow, the one Lipschitz constraint. All this really means is that the critic's function can't change too wildly. If we don't enforce this rule, the whole thing just breaks. So how do you actually enforce that rule? The best way we found is to use something called a gradient penalty. This gives us the WGAN GP model. Let's look at this loss function. The first part is just our water stand distance. That's the earth mover's cost we're trying to minimize. The second part is the penalty, and this is the magic ingredient for stability. Here's what it does. It picks random points between real and fake images, checks how steep the critic's function is, and if the slope isn't a nice gentle 1, it penalizes it. This one addition made WGANs way more stable and just so much easier to get working. Okay, so we've got the math sorted out. We've got a much better loss function. But a great loss function is useless without a great engine to run it on, right? So in section 3, let's talk about the architecture. How do we actually build these networks to turn all this cool math into amazing pictures? And that brings us to a huge milestone, the Deep Convolutional GAN, or DCGAN. Now, this wasn't about some fancy new math. It was pure, brilliant engineering. It was a set of rules, a blueprint that just worked. It gave us a reliable playbook. Use these special transposed convolutions to make images bigger, ditch the old pooling layers, and use batch normalization everywhere to keep training stable. DCGN basically became the standard, the reliable workhorse that almost everyone started using as their foundation. So, now that we have stable GANs, the community could start getting really creative. People started asking bigger questions, like, okay, can I turn a photo of a horse into a zebra? But here's the kicker. What if I don't have matching pairs? What if I just have a bunch of horse photos and a completely separate bunch of zebra photos? And that question leads us straight to the magic of CycleGAN. Yeah, the whole point of CycleGAN is what we call unpaired image-to-image translation. Let's say you have a folder full of photos, we'll call that domain X, and another folder full of Monet paintings, domain Y. No direct pairs between them. CycleGAN actually learns two generators at once, one that tries to turn photos into paintings, and another that tries to turn paintings back into photos. And of course, each one has its own discriminator checking its work. But wait a second, how does it know to change a horse into a zebra and not just some random blob? The secret, and it is so clever, is something called cycle consistency loss. The idea is beautiful in its simplicity. It says, if you take a photo, translate it into a Monet painting with your first generator, and then translate that painting back into a photo with your second generator, you should end up right back where you started. This simple rule forces the network to only change the style, because it has to be able to reverse the process and get the original content back. Okay, so we've got stability, we can translate styles. What's next? Well, the holy grail is control. Real, fine-grained, artistic control. How do we tell a GAN, hey, make me a face, but make it looking to the left, with blonde hair and a smile? Answering that question, that's the domain of StyleGAN. So in a normal GAN, you start with a bunch of random numbers, a vector we call Z, and you feed it straight into the generator. The problem is that Z space is a complete mess. It's all tangled up. You move a little bit in one direction to change the hair color, and suddenly the person's age and the background change too. StyleGAN's brilliant idea was to stick another network in between, a mapping network. This network takes that messy Z vector and transforms it into a new, much cleaner space we call W. And the magic of this W space is that it's disentangled. Now, one direction cleanly controls pose, another direction controls hairstyle. It's all separated out. And for control, this was a monumental leap forward. So how does it actually use this new clean W vector? This is super cool. Instead of just feeding it in at the beginning, StyleGAN injects this style vector at every single layer of the generator. And this is where the amazing control comes from. If you inject the style into the first few layers, the lower resolution ones, you control the big things, like pose and face shape. Inject it in the middle layers, and you start changing medium-level features, like the eyes and nose. And if you inject it into the very last, high-resolution layers, you're just tweaking the fine-grained details, skin texture, lighting, the color palette. It gives you this incredible hierarchical control over the final image. All right, for our last section, let's pull the camera back and look at the bigger picture. Because as amazing as GANs are, they're not the only game in town. To really see where they shine and where they don't, we need to talk about the generative trilemma. So this trilemma is basically the idea that in generative models, you can't have it all. You have to make a trade-off between three things: how fast you can generate an image, how good and high quality that image is, and how much variety you can produce. Now, look at where GANs sit. They are the undisputed champions of speed and quality. They can spit out incredibly sharp images in a single shot. But their weakness? That variety. They can be unstable and sometimes they get stuck in a rut, what we call mode collapse, where they only learn to make a few kinds of faces instead of all the possible faces. And that's different from, say, diffusion models, which have amazing quality and variety, but are so slow to generate a single image. So let's just recap the journey we've been on. We started with a broken system, right? A vanishing gradient caused by a flawed distance metric. The fix was a whole new way of thinking, the Wasserstein distance, made practical with a gradient penalty. Then we saw how the architecture evolved to match. We got the solid, reliable blueprint of WGAN, which opened the door for incredible applications like CycleGAN, and finally led to the insane level of artistic control we see in StyleGAN. That's the path from a frustrating idea to a true creative powerhouse. And all of this leaves us with a really big question. For a long time, GANs were king of the hill for photorealism, no question. But now, diffusion models are here and they offer stunning quality and stability, even if they're slow. So is that it? Is the adversarial game, this whole cat-and-mouse dynamic that drove so much innovation, is it over? Or is there another breakthrough just around the corner? A new idea that's going to completely shake things up all over again? What do you think?